Hello everyone, welcome to a fresh new lecture on the topic Multirate Signal Processing 1. This is Dr. Anirban Dasgupta and let's get started. So, this is a system and we all know that this is basic stuff, and we input a signal to this system and we get an output y of n. So, now if we see, this looks a pretty simple system, and this system may be linear, may not be linear. So, H is some transformation which transforms my input x n to y n. Now, in this case, both the discrete time signals operate at the same frequency. By frequency I mean the sampling frequency or the sampling rate. But imagine a system where the input and output sampling rates are different. Like input sampling rate is f of x, output sampling rate is f of y, and my fx and fy are different from each other. So, this kind of systems is called a multirate signal processing system. So, here it involves manipulation of signals at different sampling rates. So, visually if you see, if I have a sine wave of 50 hertz and I want to sample it, so the Nyquist rate will be twice 50, which is 100 hertz. But if you see, this 50 hertz can be sampled at different rates, like it can be sampled at 200 hertz, it can be sampled at 500 hertz. So, what is the big deal? The big deal is that this 500 hertz sample or sample rate is giving a better structure of the original analog signal. However, it comes at a cost of 500 samples. Now, if each sample is your say 32 bit, then this will be the total memory size. On the other hand, the signal sampled at 200 hertz captured much less information, but this is good enough to reconstruct it based on Nyquist, but it will take less size. So, if you clearly see, this version is better for transmission and storage, whereas this version is better for analysis. Also, computation complexity will be less in this version because of less number of samples, but information is more at the 500 hertz sampling rate signal. So, where is this multirate signal processing used? Now, this is used typically at analog to digital and digital to analog converters. So, when I am recording this video, I am not only recording my video, that is a sequence of images, but I am also recording my sound, and my audio is probably recorded at 48 kilohertz, and my video is recorded at say 30 frames per second. So, you can see that these two are quite different to each other. So, my frames are coming at 30 frames per second, whereas these audio signals are coming at 48,000 such samples per second. Now, when you are listening it together. So, the systems or the hardware which are doing this kind of operations, they are operating at different sampling rate. So, this is a typical example of a multirate signal processing system. Now, sometimes in audio processing like mixing, so this you all listen to a lot of songs. So, these songs, the vocals are might be recorded at different sampling rates because the voice has a different bandwidth, whereas the instrumentals can be recorded at different rates because they have a higher frequency content. So, finally, they are combined. So, that is also a case of multirate signal processing. Then interpolation. Interpolation is somewhere you have less samples and you want to find the value at the middle of some sample. So, then efficient filter implementations. So, using multirate, I can efficiently implement specific filters. Multirate signal processing also forms the basis of filter banks. And finally, discrete wavelet transform which is a very important tool in time frequency analysis, uses inherent multirate signal processing. So, now let us try to understand the methods of multirate signal processing. To recap, this is our multirate signal processing system, and here you can see that I have written y of m. Some texts write it y of n, some write y of m. I have written y of m just to signify that this is not the same index which is obtained by sampling the signal at f of x, which index was n. But for simplicity you can also use n, does not really matter. So, we can represent my output frequency f of y at some scalar value alpha times my f of x. And now, what is my alpha? Alpha can be either rational, like twice of f x, 2 by 3 of f x, and here there are some specific case of rational, like it can be integer, like alpha is 2, which means f of y is twice f of x. I am just doubling the sampling frequency. Or it can be 1 by m, like 1/3 of my original sampling frequency. Or it can be any rational fraction L by m, where L and m are positive integers. So, here integer means positive integer, of course, and then alpha can also be arbitrary, like I can select f of y as some arbitrary number 1.31 f x, or I can choose f of y something random like 1024, and f of x can be something random like say 160 say. So, there is no clear relation with alpha here, although it looks like a rational factor, but I am free to choose any, I can even choose a decimal. So, if I want to choose alpha as arbitrary, then this is the method to convert the sampling rate, which is I will first pass the digital signal which is sampled at f x through a DAC. Now, when I pass through a DAC or a digital to analog converter, it becomes an analog signal again, and then I will resample it using an ADC at Fy. So, Fx to analog and then analog to Fy, and here I need not have any specific relation, I can choose my Fx and Fy arbitrarily. But this conversion may introduce lot of quantization errors because of this repeated ADC and DAC stages. So, another is directly performing the sampling rate conversion entirely in the digital domain, and this is possible only for these 3 types, and in this module I would restrict these 3 cases. So, first let us understand what are the 2 forms of frequency rate conversion. So, either since f of x is not equals to f of y, I can have either f of x or f of y I would say is greater, or f of y is less than f of x. If it is equal, then it is no more multirate. So, here when I am increasing the sampling rate, this process is called upsampling, and when I am decreasing the sampling rate, it is called downsampling. So, what an upsampler does? So, upsampler will insert zeros in between samples, and in this way it will increase the sampling rate. For example, if this is my signal x equals to 352 and I want to upsample by a factor of 2. So, I want to increase the sampling rate twice. So, I will insert 1 0 in between each sample of my xn, and this is how it is represented symbolically, and this is the equation where y of n is x of n by 2 for n even, because this is an integer index, and for n odd I would have the signal values to be 0, and this is a graphical representation that I have this signal which is having 3 samples, and in the upsampled case I insert 2 zeros here. So, what happens to the signal in the z domain. Let us try to figure out. So, this is my signal and this is my 0th index. So, if I upsample by 2, what I do is I am plugging in zeros in between every sample. So, if I take the z transform, what happens to my xn? This becomes my xz, which is this. So, this is my 0. So, no power of z. Then my first component has z power minus 1, z power minus 2 and so on. What happens if I do to the y? Now, y we have, since there are zeros at the odd values of n. So, here the odd powers of z will be missing. Now, if you clearly compare these two, we see that only change is that the power of z is doubled. See? So, I can conclude that if I upsample a signal by a factor of 2, my spectra y of z will be x of z squared. We can obtain the same thing analytically, like, because this is just an example, but analytically you will get a very general idea. So, this is my z transform of y of z, and what is y of z or what is y of n? Y of n will be x of n by 2 for even n, right, and for odd the values are 0, because I have plugged in zeros at my odd values of n. So, here what will I do is I will replace n by 2 as some dummy variable m. So, here n becomes twice m and n by 2 becomes m, and this is nothing but the z square transform of x m. So, verified by both the methods. So, what will happen to the Fourier transform by upsampling? So, we know Fourier transform or DTFT in this case is z transform evaluated at e power j omega or the unit circle. So, we know that z transform will be x of z square, and plugging in z equals to e power j omega, I get this value, which means that this is nothing but twice of this omega. So, my output spectra y of omega is nothing but x of twice omega, which means the spectra is squeezed to half if I upsample by a factor of 2. Now, this is interesting. So, you might be tempted to say that if this is my spectra of x, then this should be my spectra of x of 2 omega, and this is my spectra of y, correct? Wrong. Why wrong? Now, see, this is from pi to minus pi, and this is just the period of the infinitely varying frequency. So, you can see that this spectra is repeating after every 2 pi. So, if you see this, so only this fundamental spectra, the fundamental period within minus pi to pi is not just squeezed. Everything, every infinite band is squeezed. So, you have here, everything is squeezed. So, technically you will get something like this, like this, like this, right. So, hence this is your actual spectra, because it will be now periodic from minus pi by 2 to pi by 2. So, what I eventually get is these are extra repeated copies, and this is called a spectral image, which is unwanted. Okay. So, in general, if I do an n-fold upsampling, then what happens is my signal is represented as x of n by L, where n is a multiple of L, because at other values of n, I am plugging in zeros, and this is the symbolic representation of this upsampling process, and this is the example. So, if I upsample that signal which I gave as an example, so I am plugging in 3 zeros for upsampling by a factor of 4. So, in general, if I upsample by L, I have to add L minus 1 zeros in between two samples of my input signal. So, some remarks on upsampling. So, first of all, no information is lost in upsampling. Secondly, the upsampler introduces spectral images, that is copies of the spectrum. So, in upsampling by 2, we had seen that one extra copy is replicated or one extra spectral image is formed. And if I am upsampling by L, so L minus 1 extra copies will be formed. Again, this is very important, the system is linear, but it is not time invariant because of this playing with the factor of n. Now, similarly, we will study downsampling. So, the downsampler will keep every mth sample. For example, if this is my signal and say this is my 0 index, so I will keep every sample. If I am downsampling by 2, I will skip every sample and retain the other. So, say there was a 4 here probably which is missed out. So, this is what I get. So, this is the symbol of downsampling, and this is also a representation of downsampling by a factor of 2. Now, if I see the signal in the z domain just like we did for upsampling, so we are discarding some alternate samples here if I am downsampling by 2. So, this is my y of n. Now, clearly x of z is easily represented from this. So, this is index 0. So, 5, 2 z inverse, 9 z power minus 2 and so on, very clear. And if we do the same for y of z, then this is my index 0, this is 9 z inverse, this is 4 z minus 2. Great, that sounds so nice. Now, how do I represent y z in terms of x of z? Because we have some extra terms like this 3 z, then this what else, 2 z inverse. So, all the odd powers of z are not appearing in my y of z, right. So, I need to somehow delete those. So, one way is to do a x of minus z, and that is what I have done here. So, x of minus z will negate all these values. So, this value, this value, this value, all these will be negated. And what happens when I negate this? Now, if I add them, I can easily cancel them, and that is what I have done. And by doing so, I am just retaining the even powers of z, and since I am adding them twice, so it is a 2 times this, which is y of z square. So, now how do I get y of z back? So, first of all, I bring these 2 in the denominator and then do a square root of the z. So, y of z will be x of square root of z or z power half plus z power minus half by 2. Now, this may appear to look complicated, although the derivation is straightforward, but you will slowly get acquainted with this. Now, z is done, what to do with the Fourier? And again similarly, I will evaluate Fourier by giving the value z equals to e power j omega, which gives me this relation, and doing the maths I get this, and by using the property finally I come to the conclusion that my output spectra is x of omega by 2 plus omega minus 2 pi by 2. And what does it mean? The frequency spectra will be spread out, it will be enlarged like this, and that is what is happening. So, this is your original spectra from negative pi to positive pi, and again as I said, this is just a fundamental period, this is occurring infinite times. Now, each will be spread out, but we know that this digital frequency has to be periodic within the span minus pi to pi. So, all this which is outside this minus pi to pi after the spread will be clipped off, and this is obvious because suppose if I signal bandwidth is say 100 and I have done something like sampling on 300. Now, this is safe because this is above Nyquist, which is Nyquist is 200, twice of this bandwidth. and this is above Nyquist, but when I do a downsampling by 2, I am getting 150, which is sub Nyquist. So, there will be aliasing, and this is a problem where we get or we might get aliasing, and this aliasing is a problem because you cannot recover the structure. So, this is a problem with downsampling. So, in upsampling we saw that we are getting extra copies, in downsampling we are encountering the problem of aliasing. We might encounter, it is not always that we will encounter, but we might. Like say if my initial frequency was 1000 sampling frequency, and if I downsample by 2, I will get a sampling frequency of 500, which is still above Nyquist. So, aliasing will not occur. Like even after the spread, it will be within the minus pi to pi range. So, in general, if I do an m-fold downsampling, so it will keep every mth sample and discard the m minus 1 samples, and this is the symbolic representation. So, this is an example. So, if I do a threefold, so this is 2, this will be probably, so it will discard this and this. So, this should be 4, and then it will discard this, and say if there is a value here, say 3. So, here you will get a value 3, and again this is 0. So, it will discard 2, and here say if we have a value say 6. So, you will get a value here 6, like this. So, in general, whenever we are doing downsampling, information is lost because we are discarding samples. Now, how big is that loss is a question. Now, again the downsampler is linear, but not time invariant, just like the upsampler, and it may cause aliasing. Okay. So, how to solve these two issues? So, here we will learn two more concepts, the interpolation and decimation. So, in general, say I have a signal like this, this and this. Let me use a separate color. So, if I use green, and say I have a 0 in between. So, this is because of interpolation. So, initially this looks like a signal which is not good as the original stuff. So, if I do, I need some interpolation, I need some value which is not 0, which is some value somewhere in between. Like if I do a linear interpolation, let me pick another color like blue, and if this value should be somewhere here and somewhere here, now this gives me a smoother estimate, and that is interpolation. So, how to do a smoother estimate? I can always do a low pass filtering, because in smoothing in time domain we studied that what is smoothing, low pass filtering, because it will remove this sudden change to zeros to a smoother value. So, this can be done by using a low pass filter. So, the low pass filter should be before the upsampler or after the upsampler? It should be after the upsampler. Why? Because if you see the frequency domain, what it is doing is, if this is the spectra, it has created extra spectral images. So, I need to remove this, and I have to retain this. So, I can create a low pass filter which will just retain the main component, and you can see after adding zeros only I am doing the low pass filtering. So, this is called an interpolation, that upsampler combined with the low pass filter. So, this is an example. So, I have a signal, I upsampled by a factor of 2 by inserting 0 in between, and then I did interpolation, like I did a low pass filtering, the total thing is interpolation, and now see I get a very smoother response. And again it depends on the design of the filter, that what kind of response I will get. Similarly, in decimation we combine a low pass filter with the downsampler, and here you should note that the low pass filter is kept before the downsampler. Why? Because the downsampler, what it is doing is it is spreading the spectra, so that it is going and aliasing. So, this is like an anti-alias filter. So, this anti-alias will restrict the frequency range of the original signal before the downsampling process. such that information is not lost. So, this is what we are getting in the decimated system. So, we have to do this before downsampling actually. This downsampling is, so first we will do the decimation filtering and then we will do the downsampling. So, we have now understood that if my f y is some L times f of x, which is the case of my upsampling, and also the case where it is 1 by m times f of x, which is my downsampling, and we also covered interpolation and decimation. What about fractional rate, like if it is L by m, which is a rational number, how to do it? So, we can always first do an interpolation by L and then do a decimation by m, or we can do a decimation by m and then interpolation by L. So, I request you to pause for some time and think which is a better strategy. So, clearly you can think that if I do the interpolation first and then decimation, this is a better strategy. Why? Because in interpolation you are adding some samples and then you are discarding. So, information loss is less. But if you do the decimation first, you are at the beginning only discarding some samples and losing away information and then doing the interpolation. And this can be also efficiently defined by seeing the block diagrams. So, this is an interpolator where we have an upsampler and then this low pass filter, which gives me an intermediate variable or signal p of n, and this p of n, if I send it to another low pass filter and then the downsampler, which is basically the decimation system, and I can get the output. Now, here the good thing is that since this is a linear filter, this is also a linear filter and they are in cascade, I can combine them into a single filter. So, I do not need to design two filters, I can get away with a single filter. So, I will have an upsampler first, then this filtering will do both the things. That first is it will remove the spectral images of this upsampler and also it will do the anti-aliasing for the downsampler. And how do you design the cutoff frequency? So, the cutoff is designed such that it will be minimum of pi by L and pi by m, and this design ensures that you both eliminate the spectral images and also avoid aliasing. So, thank you so much. We will meet again in the multirate signal processing lecture 2.